Hello, we're now going to follow on directly from the demonstration Francois presented earlier. Here we will see how we can run the same tests on the target hardware and also get timing information. This is the RVS Project Manager. From here you can configure and run your RVS projects. However, everything I'm going to show you can also be done on the command line, making it easy to integrate RVS with an existing continuous integration system. These are exactly the same test definition files used with SCADE earlier. Wrappy tests can read them and generate a test harness that can be run on target. In order to do this, we use a compiler wrapper. This program lets us intercept calls to the compiler so that we can add timing instrumentation and test code before passing the modified source to the real compiler. This removes the need to make any changes to the build system. We're now going to run the tests on the target, which is an STM32F4 ARM microcontroller. The tests have completed and we're now downloading the results using a JTAG debugger. That's not the only way we can extract the data. It's possible to use serial or Ethernet or any other interface that you have for communicating with your target. RVS is now processing the test data and the timing traces in order to generate a report, which will open automatically as soon as the process completes. The first screen the user is presented with contains the test results. Here we can confirm they match the result obtained from the model. The results from individual tests can be expanded to view more detail, and we can also check the reason for any failures. Next, we can see the timing analysis results. For each function, we report the minimum, average, maximum, high watermark, and worst case execution times. The first 5 metrics are extracted directly from the trace data. The worst case execution time, however, is calculated by examining all possible paths through the code and combining these with the measured execution times of each block of code. As you can see, the worst case execution time is higher than any execution time observed in testing. To understand why this is the case, we can compare the slowest observed path, highlighted in purple, with the predicted worst case path, highlighted in blue. When both paths are highlighted, the observed path is drawn on top of the worst case path. This allows you to quickly identify code that is on the worst case path but not on the slowest observed path. You can then add additional test cases to hit these paths, and these tests can first be run on the model before checking the correlation on the real hardware. Rapita provides a wealth of data about your system. For each block of code, we can see its execution time profile, which shows the frequency that certain times are exceeded, as well as the distribution of execution times. Here there is a nice normal distribution of time on the left, but there are some outliers on the right that are more than twice the average execution time, and this may be cause for concern. Rapita can also show you the order in which events occurred during the test. The Invocation Timeline shows when every function call occurred, as well as highlighting the maximum times. Sub-function calls are also shown in order, and we can zoom in to view more detail. We can also directly play back the execution traces, stepping through each instrumentation point as well as into and out of functions, just like a debugger. However, unlike most debuggers, we can go backwards as well as forwards, as sometimes the reason for a timing overrun was caused by the previous iteration. We can export the timing and test data from the report in a variety of different formats. Like SCADE, we offer a qualification kit for all our tools that includes and allows for a qualified export of timing and test data for submission to certification authorities. Finally, if you have any handwritten code, such as startup routines or device drivers, that is not part of the model, we can also measure the code coverage of this on host or on target using Wrappy cover. This concludes the process of back-to-back testing, first directly on the model and then on generated code running on the real hardware.